flipped classroom presentation for Further Maths Unit 5, Hypothesis Testing 1. We extend the procedure of hypothesis testing introduced in Maths Unit 4 to the testing of a specified value for the mean of a distribution given a large sample, not necessarily normal, with sigma unknown, and a specified difference between the means of two normal distributions with sigma unknown. So sigma unknown with just testing of the mean. It will be assumed that you are familiar with the following terminology introduced earlier: null and alternative hypotheses, test statistic, critical region, p-value and significance level. We'll come across them in the questions. A null hypothesis is the statement that the value of a given parameter is equal to a given value, theta 0. An alternative hypothesis would be the statement that the value is in reality less than, greater than, or not equal to the value given in H0, the null hypothesis. If the alternative form of the if the hypothesis is of the form greater than or less than, then it's called one-sided. So our p-value would be the tail ending of the probability. Is the tail ending small enough that we can reject H0? But if it's of the form not equal to, then it's two-sided. So we have two lots of the probabilities that we need to add up. If the p-value is the probability that the observed result or a more extreme one will occur under a null hypothesis, then we use the interpretations that if it's less than 0.01, less than 1%, there's very strong evidence for rejecting H0. If it's between 0.01 and 0.05, then there is strong evidence for rejecting H0, between 1% and 5%. If it's greater than 0.05, 5%, there is insufficient evidence for rejecting H0. We cannot reject H0. A pre-specified value for the probability of rejecting H0 when it is in fact true is called a significance level. That is the cutoff where we either reject H0 or accept it. And it's usually denoted by alpha. The significance level is often quoted as a percentage. For example, if alpha is less than 0.05, we say that the test should have a significant level of 5%. So either 5% or 0.05. So the p-value was the end bit. The point at which the p-value is the cutoff is called a critical value. That's the maximum or the minimum, if it's the other side, for theta that we reject H0, the critical value for rejecting. The critical region is a set of values of theta, so the theta for that the number of successes mean we reject H0. So the critical region is above the critical value or below. Now we're going to test the mean of a distribution of a large sample with sigma unknown. So let X denote a random variable whose distribution is not known. Denote its mean by mu and its variance by sigma squared, which we don't know. The random sample of n observation is to be used to test the null hypothesis that mu is equal to mu naught for some specified value. We shall assume that n is large enough to justify using the central limit theorem. And the central limit theorem states that if x bar is the mean of a random sample of observations of the random variable x, whose mean is mu and whose standard deviation is sigma, then for large n, the sampling distribution of x bar is approximately normal. So the mean value of the sample has a normal distribution. Then, as we did in previous work, we can approximate the sampling distribution of the sample mean x bar by the normal distribution having mean mu and variance sigma squared over n. Therefore, if x is normally distributed by mu and sigma squared, then x bar is going to be normally distributed. And for the unknown bias, for unknown variance and unbiased estimator of sigma squared is this one, which we've done before, or this one, or this one. And it's usually easier to use the second or the third formula for estimating the variance of the population. Right, so if you have an example, the records of the heights of a policeman in a certain force in 1985 show that their average height was 185 centimetres. The question was posed as to whether the average height of policemen in the force in 1995 was different from that in 1985. To answer this question, the heights of a random sample of 60 policemen in the force in 1995 were measured in centimetres. Analysis of these heights give unbiased estimates of the population mean and variance equal to, so the sample mean was 182.5 and the sample estimate was 22.64. So estimate of the mean and estimate of the variance were those. Carry out an appropriate test to answer the question posed. So we have to set up x being the height of a randomly chosen policeman in the force, and mu denote the mean height of the policeman in the force, the population mean. So an appropriate null and alternative hypotheses are that mu is equal to 185, i.e. there's no change, against H1, that mu is not equal to 185, that there has been a change. Assuming that 60 is large enough for the central limit theorem to apply, and the sample unbiased estimate of the population variance be reasonably close to the true value, then the sampling distribution of the mean height is now going to be approximately normal. It never mentioned normal at the beginning, but being as we've got a large sample, then the sample mean is going to be normally distributed with mean, mu, which we don't know, and s squared over n, so 22.64 over the 60 for the variance of the sample mean. Since H1 is two-sided and the observed value of x bar is 182.5, which is less than 185. So we're looking to work out, we need the two endpoints, but being as our sample value, our observed value, is below 185, I'm looking at this side to start with. Then I'm going to double the population. Is 182.5 small enough to say that there has been a change? So I'm changing my 182.5 x bar into z's, and I'm getting 182.5 minus 185 for the mean over the square root of the variance of x bar, which becomes that. Then our z is going to be less than or equal to minus 4.07, which I work out either on the calculator or from tables, and then I double because it's a two-sided, so it could be less than or more than. So I've got 0.00006, which is less than 0.01. So very strong evidence against H0. So we can conclude confidently that the mean height of the policeman in 1995 is different to the mean height in 1985. Example 2. A shopkeeper complained that the average weight of a certain packet of biscuits that he buys from a wholesaler is less than the stated mean of 227 grams. The shopkeeper weighed 100 packets and found that their weights had mean of 226.8 and standard deviation 0.72. So that was the sample estimates. Determine whether the shopkeeper is justified in his complaint. So let X bar denote the weight of a randomly chosen packet of biscuits, and mu denote the mean weight of the packets of the biscuits overall. So an appropriate null and alternative hypothesis are that mu is equal to 227 grams, there's been no change, or that it's less than 227, making that there is a change. Assuming that 100 is large enough for the central limit to apply, and the sample unbiased estimate of the population variance is reasonably close to the true value. Then, the sampling distribution of the mean weight X bar of 100 packets is approximately normally distributed now then, with mean mu and variance 0.72 squared over 100. Since H1 is one-sided, then now p-value is just X bar, probability X bar is less than 226.8 when the mean is 227. That's what we're testing. So changing that to Z, 226.8 minus 227 divided by the square root of the variance, which is 0.72 over 10, giving us Z less than or equal to minus 2.78, and its probability is 0.0027. This is less than 1%, so very strong evidence against H0. We can therefore very confidently conclude that the mean weight of a packet of biscuits is less than the mean stated weight. Example 3. If you're given now the significance level, a researcher for a manufacturer of string has claimed that a particular type of coating applied to the string would increase its mean breaking strength from its present value of 7.2 kilograms. A coating was applied to a random sample of 60 pieces of string, and their breaking strengths were such that the sum of x was 456 and the sum of x squared, each squared value of x, the sum of those was 3540. Using the significance level of 5%, so that's a cutoff, to determine whether or not the researcher's claim is correct. So let mu denote the mean breaking strength of the coated pieces of string, and we need to test that mu is 7.2 against mu is greater than 7.2. So let X bar denote the mean breaking strength of the random sample of 60 pieces of string. So for the given result, we've got the sum of x to be 456. So our mean, sample mean, is 7.6. And our sample variance, an unbiased estimator, would be 1 over 59 times the sum of x minus the sum of x squared, minus the sum of x all squared over n, giving me 1.2610. Assuming that n is large enough to justify 1, the use of the central limit theorem, and taking s squared as being close to the population variance, we have at our p-value, it's one-sided, is x bar is greater than 7.6 or equal to 7.6. Is that far enough away from the mean is what we want to test. So changing that to the z, as we're now using normal distribution, so it's 7.6 minus the 7.2 over the square root of the variance over n. So s squared over n, square root of s squared over n, as is the sample mean. So we are testing that z is greater than or equal to 2.76. Looking that up, we get the probability the p-value is 0.00289. The significance level was 5%. Our p-value is less than that, then we reject H0, and our conclusion is that at the 5% level there is sufficient evidence to endorse the researcher's claim. So that's given a 5% as the cutoff level. Now, testing the difference between the means of two normally distributed with known variance. So the previous one was an unknown variable with unknown variance. This is not definitely two normally distributed and with known variance. So let x and y denote two independent normally distributed random variables having mean mu of x and mu of y and standard deviation sigma x and sigma y respectively. And we want to consider testing mu of x minus mu of y is equal to some specified value delta. Most of the time it's equal to naught. That is, we are testing if the means are equal or not. Let x bar and x and y bar respectively denote the means of random sample nx of x and ny of y. Then, as x bar minus y bar is a linear combination of normally distributed variables, we know that x bar minus y bar is also normally distributed with mean, the difference in the means, and the variance would be the sum of the variance of x bar and y bar. So it's sigma x squared over n of x and sigma y squared over n of y, as we're talking about the means. Example 4. A firm has two precision grinding machines A and B, which produce cylindrical rods of mean diameter 2.50. The diameters of the rods produced on machine A are normally distributed with a standard deviation 0.01, and the rods produced on machine B are normally distributed with standard deviation 0.015. The composition of steel the firm receives from its supplier is slightly changed. Random samples of 10 rods from outputs of machine A and B had mean diameters of 2.535 and 2.552. Assuming that the standard deviations are unchanged, test the hypothesis that the mean diameters produced by the two machines will still be equal. So are they close enough for them to be equal overall? So let x and y respectively denote the diameters of randomly selected rods from machine A and B. Let mu x and mu y denote the means of x and y. We need to test, are the means equal against are they not equal? So it's going to be two-sided. We need to test them, the difference in mean. So if we bring the mu y over, we need to test, are the means, the difference in means equal to naught or not? So let x bar and y bar denote the sample means. Then, as x is distributed normally with those combinations and y distributed normally with those, then x bar will be distributed normally with a variance of 0.01 squared over 10, and y will be distributed normally with a variance of 0.015 squared over 10. These are independent, so it follows that the combination will be normally distributed with mean, a difference in means, and the variance will be the sum, as we're squaring the coefficient, would be the sum of the two respective variances, and that becomes 0.0000325. The observed value So we take away the two means and we get the observed value was minus 0.017. Since this is less than 0 and h1 is two-sided from above, so our delta is 0, so we are testing the difference in means is equal to 0. So is this value far enough away from 0? So we have our p-value is twice as it was two-sided. The difference in means, the probability of the difference in means is our observed value. Is that far enough away? So change that into z. So I've got minus 0.017 minus the 0 divided by the square root of the variance, and I get z less than or equal to 2.98, giving me a probability of 0.00144, double that, and I get 0.00288. This is less than 0.01, so that there is very strong evidence for rejecting H0, and we can conclude that they are not, the means are not equal. That is, with the new composition of steel, the mean diameter on the rods on machine A is not equal to that produced on machine B. Example 5. The random variables x and y are independent, with x being distributed normally with mu as the mean and 25 as the variance, and y being distributed normally with lambda and 16 as its mean and variance. It is required to test mu minus lambda is equal to 10 against mu minus lambda less than 10, based on the values obtained in a random sample of 10 observations and 12 observations of y. So find the significance level. So what is the value where we reject H0 only if x bar minus y bar is less than or equal to 7.5, where x and y are sample means. We'll do that first. So that's what we want to test. It's one-sided, so the significance level is of the given decision rule. So the decision rule is x bar minus y bar less than 7.5. We want to test that probability when H0 is true. So 7.5 minus the 10 over the square root of 25 over 10 for the variance of x bar and 16 over 12 for the variance of y bar. Square root of those, so I get z less than or equal to minus 1.28. Looking that up, its probability is 0.1003. So that is the significance level. That is the value where we decide if they are equal or not. If they are, the difference is equal to 10 or not. So the observed value, so part B now, given that the observed values were those two, what conclusion should be drawn if the significance level is 5%? So we have two values, so their difference in means gives us 6.76. Then the p-value is now that we need to test 6.76 when the difference in means should be 10. So 6.76 minus the 10 over the square root of the combined variances, and we get z is less than or equal to 1.65. So looking that up, I'm getting 0.0495. So this is less than the 5% significance level that we were quoted. So we reject H0, then the difference in the means is less than 10. Example 6. X and y are two independent, normally distributed random variables, each having standard deviation 5. The means mu x and mu y respectively of the distributions are unknown. It is required to test that the difference in mean is equal to 2 against the difference in mean is greater than 2, and using values obtained in random sample of 50 observations of x and y. So find the significance level of the decision rule, which will reject the difference in means being greater than or equal to 4, where x bar and y bar are the sample means. We'll do that first. So that's what we need to test. Given x, we need to define x and y as the values. The first is normally distributed with mean mu x and variance 25, and the second one is also got variance of 25. Both are normally distributed. Then x bar and y bar will have mean, the difference in the means, and the variance would be the sum of the two variances divided by the ends of each one, and that becomes 1. So the variance of the combination of the means is 1. There's a significance level is what we need to find. We are given that is what we need. That's the rule, the decision rule, when h naught is true. So that changing into z gives us 4 minus 2 over the 1, which is greater than or equal to 2. Looking that up, and we get 0.02275. So that is the significance level for that decision rule. That is the level at which you reject h naught. Part B. Find the decision rule this time if the significance level is to be 0.01. So we need to specify a value, c say, a critical value, and the significance level of this rule is following the same pattern. So the probability of the difference in means being greater than or equal to c when h naught is true. So changing to z, so c minus 2 over 1. I need the 1%. The significance level is 0.01, so 1% would be in the tail end. That's my significance level. So what is the critical value? What is the rule, decision rule? So looking that up, either from tables or your calculator, so we can see that we get a value of z to be 2.3263. So rearranging, we get c to be 4.3263. So our decision rule for a 1% significant level would be that x bar minus y bar is greater than or equal to 4.3263 or 6. Part C. Given that the observed sample means were those two, find the significance level for h naught to be rejected. Okay, so smallest, the sample level, the sample gives us difference in means to be 3.7. Then the p-value is the probability of x bar minus y bar being greater than or equal to 3.7 when h naught is true, i.e. when x bar minus y bar is equal to 2. So rearranging into z's, I get 3.7 minus 2 over 1, giving us a p-value of 0.0446. That is the significance level. So for the observed sample means h naught should be rejected only if the chosen significance level is greater than that value, i.e. 4.5%. And that is the end of the presentation on hypothesis testing 1.